Hi everyone, this is Mrs. J, and today we're going to be reviewing exponential and logarithmic functions. Before we start, I have a quick warm-up for you guys, so if you could pause the video and give it a try, you can hit play when you're ready to check. Alright, go ahead and check your work here. So again, this is just evaluating a logarithmic expression, so essentially understanding what a logarithm represents. So for any logarithm, the base of the logarithm is essentially the base of your exponential term, and the logarithm is going to define what the exponent is if this is the result. So we're essentially asking 3 to what power is 1 over 27. We know that if we cube 3, we get 27, and to cause that reciprocal action, we make our exponent negative. Here we're essentially asking 9 to what power is 3. And I know that, well, the square root of 9 is 3, and we know square root happens when we have a rational exponent of 1/2. And then here, this is a natural log. Remember, they're base e. So we're essentially asking e to what power is e to the power 5? Well, then that must be 5, just by logic. And here, 1/2 to what power is 1? Anytime it's the log of 1 of any base, the answer is going to be 0, because anything to the power of 0 is 1. All right, so here is the definition of a logarithm, so it kind of reviews what we just did in the warm-up. So if you have an exponential expression b to the power of x equals a, we could rewrite that as log base b of a equals x. So notice that the base of your exponential term is the base of your logarithm, and the exponent is what your logarithm is equal to. So I always remember that logarithms define exponents. Also remember for both of these forms, the base must be positive and it cannot equal 1, just by definition. Two kind of special logarithms that have their own notation. A base 10 logarithm, we call it a common log. We typically don't write the base 10. So if you ever see the log without a base, it is a base 10 or common log. And then a base e logarithm, we call a natural log. We write it like this, so ln of x. We still read it natural log, but it's important to know it's just a base e logarithm. All right, so now I want to look at some parent functions of our exponential and logarithmic functions. So here I have the parent function for e to the power of x, and here I have the parent function for natural log of x. They all, depending on what your base is, it will look a little bit, it will change your graph slightly, but they'll all have the same general shape and characteristics. So for your exponential functions, first of all, they're all going to go, your parent functions will all go through the key points 0, 1, because anything to the power of 0 is 1, and 1, and then whatever your base is. In this case, it's 1e, because e to the power of 1 is e. And then they will all have a horizontal asymptote at y equals 0. So if you know those two key points and where your asymptote is, you can transform your graph depending on what transformations you see in your function. Same for our natural log function, so it's important to know kind of this general shape that they make. And they will all go through 1, 0, and then whatever your base is, 1. So in this case, it's e1 because it's a natural log. And our parent functions will all have a vertical asymptote at x equals 0. Now, for our exponential functions, if our base is less than 1, so if it's between 0 and 1, you'll end up with an exponential decay graph. So it looks like this. So it's a decreasing graph. And then if the base of your logarithm is also between 0 and 1, you'll have a graph that looks like this, also decreasing. But, same general shape, same asymptotes. So if you know, again, some key points from your parent function and you know your asymptotes, you can graph just about any transformation. All right, let's give a couple of these a try. So in this first one, I see that we have, our parent function would be e to the power of x. I'll write that down here. And if it helps, you can kind of sketch in what that parent function would look like. You want to, but you don't have to. But we can take our two key points from this graph, which in this case would be 0, 1 and 1e. And we could also take our horizontal asymptote from our parent function, which is y equals 0. And then we could transform it based on what we see in the graph. So here I see 3 transformations, a vertical reflection over the x-axis, a vertical stretch by 2, and a vertical shift up 3. So I'm actually going to multiply my y values by -2 and then add 3 to them. So if I multiply this by negative 2 and then I add 3, it actually stays in the same space. It's 0, 1. And then here, again, if I multiply by negative 2 and add 3, I end up with negative 2e plus 3. So this would be an exact coordinate. We can estimate that value to help us graph. And then I multiply this by negative 2 and then add 3. So it shifts up 3. So our horizontal asymptote is here. And then we have the point, again, 0, 1. And then you can get a decimal approximation for this point to help you graph. It's about negative 2.4. So 1, negative 2.4, so right around here. And our graph is going to look like this. So now it's a decreasing graph due to that reflection, that vertical reflection that we see. So here we have a pretty accurate graph just from transforming two coordinates and our horizontal asymptote. All right, let's try the second one. Here we have a natural log function. So our parent function would just be the natural log of x. So our two key points here would be 1, 0, and e1. And then we also have a vertical asymptote at x equals 0. So remember, it looks something like this. Okay, and now we can transform our coordinates or our graph, whichever way you prefer, but we do need exact coordinates, so this helps us provide those. So here I see one vertical change, so all of our y values are going to be multiplied by 1/2. So this stays at 0, this is 1/2, and this is going to be a horizontal. It will only be changed with a horizontal translation, so let's see what else is going on. So here, hopefully you remember, whenever we have a horizontal stretch or shrink or a reflection, we do need to factor it out from the rest of our graph. So we have to factor out the negative, and then it becomes this, x minus 2. So this graph here, or for this function, we have two horizontal transformations. Horizontal reflection, so it's going to go over the y-axis, and this is actually going to shift to the right 2. So we're going to multiply all of our x values by negative 1, and then we're actually going to add 2 to them. So again, here, when I multiply this by negative 1 and then I add 2, it actually stays the same, kind of a coincidence. And then here, this just becomes negative e plus 2. So that's our exact coordinate. And this becomes x equals 2. We multiply by negative 1 and then we add 2. So remember, this is actually shifting to the right 2, even though it says minus. So if we want to shift something to the right, we would add to the x values. And we will want a decimal approximation for this coordinate. So it's going to be about negative 0.7 more or less. Okay, so now let's plot what we have. So our vertical asymptote is at x equals 2, and then we have, again, the coordinates 1, 0, like this, and negative 0.7, 1/2. So right around here, you kind of just have to estimate. And then our graph looks like this. So you could see that the reflection, horizontal reflection is what's causing it to now become a decreasing graph, and then it has also looks a little bit flatter than our original graph and has been shifted to the right too. So there you have it. So again, if you know some key points from your parent function, you can graph just about any exponential or logarithmic equation. All right, so the next thing I want to review with you guys are the properties of logarithms, which are going to be really useful when we start solving logarithmic equations and a few examples. So there's 3 important properties to know. The product property tells you that if you have the logarithm of a product, we can actually expand it into the sum of 2 separate logarithms. So notice that we have the log base b of m times n, the product of m and n. It becomes the sum of log base b of m plus log base b of n. So notice that the bases of both of these logarithms are b, and here m and n are within our individual logarithms. So notice, that the log base b of m times n is not, absolutely not equal to the log base b of m times the log base b of n. The product of within a logarithm is not equal to the product of two individual logarithms. I also want to point out that for all of these, you can kind of go either way. So sometimes we kind of do the reverse. We take two individual logarithms and we condense them. So if you have the sum of two logarithms with the same base, you can condense them into a single logarithm with a product. So again, here, notice that the log base b of m plus the log base b of n is absolutely not equal to the log base b of m plus n. You can't just add within the individual logarithm. It becomes a logarithm of a product. So the quotient property is very similar. If you have a log with a quotient within it, you can actually expand it to the difference of two different logarithms. So log base b of m minus log base b of n. I always just like to remember that anything that was in the denominator within my logarithm becomes a negative logarithm. You don't have to write it in this order, but this logarithm will always be the negative one, and this logarithm would be the positive one. The last one, which is a really useful property, is called the power property. It says that if you have a logarithm of a term with a exponent, you can actually just take that exponent and you can put it right out front of your logarithm. Or vice versa, you can take a coefficient of a logarithm, and you can move it up to the exponent, which can also be really useful when we're solving equations. And then here's another important formula that you should know that we might need to help us get a decimal approximation of a logarithm. That's the change of base formula. So you could change any base logarithm into whatever base you want. So log base b of a becomes log base c of a divided by log base c of b, and c is your choice. So I will always choose a common log or a natural log because my calculator can do those things, but again, you could change it to whatever base you want. And notice this value it stays in the numerator, and the base is in the logarithm in your denominator. All right, so now we're going to try solving some exponential equations. So here's some strategies. First, you could try to make the bases of your terms the same, and if the bases are equal and the two terms are equal, the exponents must be equal. So sometimes the strategy works, sometimes it doesn't, just depends on the numbers. Or you could also isolate your exponential term, and then you can take the log of both sides, and it may be helpful when you take the log of both sides to match the base of your log to the base of the exponential term. You don't have to do this. You can take the common log of both sides or the natural log of both sides, but sometimes it's a little bit helpful. All right, so let's look at these two examples together. So here we have 2 to the power of 4x equals 32 to the power of x minus 1. So here, hopefully you notice that 2 and 32 are within the same family. They both are powers of 2. So I can actually rewrite this so the two terms have the same base. I can rewrite 32 as 2 to the power of 5. And then here, if we just distribute this exponent, now if the two terms are the same or are equal and they have the same base, just by logic, the exponents must also be equal. So you can solve from here, and we end up with x equals 5. So again, sometimes this strategy will work. Sometimes, like you see in example B, it doesn't, because there's no real way to rewrite a base 4 and a base 15 to have the same base. So in this case, we are going to want to take the log of both sides. Well, actually, there's a few different ways we can do this. So one, we could take the log base 4 of both sides, log base 4 of 15. And then when we do that, if we simplify this expression, it's actually just equal to x. So x is log base 4 of 15. So this would be an exact answer for us. Now, if we want to get a decimal approximation, we are going to need to use that change of base formula, because your calculator may not be able to calculate log base 4, but it can definitely calculate a common log. So here you could plug this into your calculator. I'll do that real quick. And you can get a decimal approximation. So again, it just depends on what type of answer you're looking for. And this is about 1.95. So Again, here's an exact answer. Here's a decimal approximation. Also, another way you can do this, you can actually go straight into logarithmic form. You could rewrite any exponential equation as a logarithmic equation. And this would be log base 4 of 15 equals x. And from there, you actually are done solving. Or just to show you some alternative ways, you could just take the common log of both sides, or whatever log base you really want. And then from here, you could use that power property, and we can move the x out front. And then we can divide both sides by the log of 4, the common log of 4. And again, you'll see that we get the same answer. So these two answers are totally equivalent. And then again, you could plug this into your calculator and you get the same decimal approximation. So there's a few different kind of strategies you could use to solve this, but they all lead you to the same place and just about the same amount of steps. All right, now the last thing we're going to review is how to solve a logarithmic equation. So again, a few different strategies. Sometimes you can isolate the logarithmic expression and then just simply rewrite it into exponential form and you can finish solving from there. Sometimes you actually need to use your properties of logarithms to condense two terms into a single term. And one thing to remember with logarithmic equations, since logarithmic functions have a restricted domain, you have to check your answer for extraneous solutions. So you have to make sure that your answers are valid, whether you get one answer or two answers, or, well, it is also possible to get no solution. So always check your answers with logarithmic equations. All right, so let's give these two a try together. So for this first one, we just have a single logarithmic term. Log base 4 of x plus 3 equals 2. So we can actually rewrite this straight into exponential form. So this would be 4 to the power of 2 equals x plus 3. And then from here, we just finish solving. So x equals 13. And of course, since again, it's very possible to get extraneous solutions, we need to check this. So we can substitute it into our equation. So we get 13 plus 3, which is 16. Log base 4 of 16 is 2, and 2 is equal to 2. So our answer is correct. Okay, let's look at part B. So for part B, I have two logarithms, so I can't really isolate them now. So I actually have to use my properties of logarithms to condense these two into one. So we can use that product property, and it will become x, the log base 2 of x times x minus 7. So now I have a single logarithm. So this would be x squared minus 7x equals 3. So now I can kind of just pick up where I started in the last example. We can just rewrite this in exponential form. And here we actually have a quadratic equation. So we're going to want to set our equation equal to 0 so we can solve. This one we can solve by factoring, and then we can use the zero product property to get two solutions, two potential solutions, x equals 8 and -1. And then we can go back and check. Now, when I plug in -1 right off the bat, so if I'm checking x equals -1, when I substitute it here, log base 2 of -1, into this first one, this is undefined. This value will always be positive because think about it, 2 to any power will always be positive. If our base is positive, the result must be positive. So I know here that this is actually an extraneous solution because again, that makes this logarithm undefined, but that does not mean that this is that this is a solution. We still need to check x equals 8. So let's substitute it in, log base 2 of 8 plus log base 2 of 1, 8 minus 7 equals 3. Log base 2 of 8 is 3. Log base 2 of 1 is 0, and we get 3 equals 3. So we do have one solution here, x equals 8. But again, you can see how important it is that we checked our answers because in this case, we did have an extraneous solution. So always, always, always double check logarithmic equations. All right, so that is all for today's video. Thank you so much for watching.